Good morning. I think we are ready to start our session. If you're ready, you can, yes, thank you. Okay. That means we went through the lesson 1, the week 1, and I am impressed with your discussion. I really like all of the posts. And if you notice, I've already almost read everything and graded. Okay, that means you can see your points. Most of the students get 5 points. If you followed and if you respect the instruction for the discussion post, you got 5 points, which means you have to post something and then like a constructive at least two replies are expected. Okay, and also what I would like you to do maybe a little bit more, use the editor equation, the math editor equation. Okay, that means you can practice typing the math symbols. Okay, but overall I am happy, and of course the average of the self-assessment quiz and the weekly quiz, the concept quiz, I mean, it's also good. Okay, that means I believe we are ready to start calculus, okay? Because lesson 2 will talk about the basic concept of calculus, which is the limits, okay? The limit concept. And this week, lesson 2 will cover section 1.4, 1.5, and 1.6. That means you can go to the textbook and try to read and solve the suggested problems. Each module, of course, the lesson module, includes the suggested problems. And also, what I did, I make like a summary page from the material which is in the textbook. That means if you think the textbook is too heavy, you may read the summary notes that I've prepared for you. Okay? And then you can practice, of course, doing the homework assignment, and then again, posting some comments, some notes on the discussion board. Okay, let's start. That means what we have. We do have section 1.4. Let's start. Basic concept of calculus. First of all, like we should know like what calculus is. That means we do have lots of branch of mathematics, lots of fields, lots of parts of mathematics. That means one of them is just pre-calculus, I can say. I mean, I shouldn't say just, no, pre-calculus, which pre-calculus, algebra, it's like more static. That's the set of tools that we can solve the problems. Yeah? We definitely need these tools. And then what we do have a calculus. Okay? Of course, we have lots of different fields. As I said, we have probability, we have the number theory, we have lots of different, like a linear algebra. We have lots of different fields, but one of them is calculus, and calculus is more dynamic. Okay, which means calculus will be the set of tools that we will create a problem. Okay, that means we will create the problems, and then in order to solve the problems, we will definitely need pre-calculus algebra. Okay, and calculus, of course, we have lots of application, we have lots of like use of that field. Okay, and we will see how we create everything. In my the next slide is, let's see how calculus, how we can get to calculus through the algebra, pre-calculus, and then I will introduce the limit process, okay, and then calculus, okay, and we do have two main parts of calculus, which is derivatives and integrals, but they are so connected. Okay, we will see it's like a circle. We will we will do something, like let's say we will differentiate, and then we will have some output, and we can anti-differentiate and get back to the original point. Yeah, that means we will learn how to do this. Okay, and then I have a few comparisons, what we can do without the calculus, and what we really, what we can't do without the calculus, okay? That means with, like, for example, let's look at the first row. We can get the value of the function, no problem, but can we really compute, like, estimate, approximate the situation, not exactly at the point, which is the value, near to the point. That means what is happening with the function, yeah, as x, this is x equals to c. As x is getting really close, we can see x will be getting really, really close to the quantity c, but it's not c. You can see we have empty dot. Okay, that means it's not c, but then what is happening with the function near to that point? Okay, that's our task, and I believe for this week. Okay, we can find the slope of the line, no problem, especially if we have 2 points given. Yeah, slope of the line, if this will be the line that is intersecting the curve, do you know the name of the line that intersects the curve twice? Secant line. Thank you. Yeah, that's mean not, yes, thank you. That means that's not a problem. We have 2 points. We can find the changes along the y-axis, the x-axis, no problem. It's like an average rate of change, I can say, or slope of the secant line. But the problem is how to find, or maybe the second line and the third line, it's almost the same thing. That's actually, I was going to focus. That's the secant line, which we actually have, because slope of the curve and slope of the tangent is almost the same. Also the topic for this lesson. But we can see, how can I find the slope of the curve or slope of the tangent line? Okay, tangent line. And actually one of the things today will be we will talk about the tangent line. Do you understand? Do you know the definition of the tangent line? Because we have to be extremely careful with this, and we will need this a lot. Yeah, that means who can tell me, or you can type? It's the it's the line that touches 1 point. It's touching the curve. Yes, on the slope, we can say this way. That we can see we do have only 1 point. Okay, 1 point of intersection, but I can't really say this way. It's not really like it's inadequate. It's using the word touching, it's better, because we can see the blue line is perfectly touching the curve at 1 point. Because if I will say, oh, this is the line that is intersecting a curve once, I can draw a line like that. And I have 1 point of intersection. Do you think my green line is a tangent line? Because I want you to have the feeling what tangent means. Do you think my green line is a tangent? Of course, yeah, you can easily guess that it's not a tangent, because it's not really touching. Yeah? It's like intersecting. We really need this touching. Like we have to have this definition, touching. And actually tangent in Latin means touching. Okay? And more precisely, mathematically, touching means that if I will zoom in, if I will go extremely close to the point that the curve is touching, the line is touching the curve, we can see we can't distinguish the difference between the tangent line and the curve. Okay, that's me. And if I will go, let's look at this circle. If I will go really close, I will always have this kind of like an X intersection. They will be always different. One line, my green line and the curve will always go in different direction. Okay, that means touching means that when we zoom in, both tangent line, which is tangent, and the curve, they go in the same direction. Okay, that means that's the reason that sometimes tangent line to the curve is exactly the same thing like slope of the curve, because they are the same. And we can see the blue line is simply a tangent line looking at here. Okay, okay, that means we understand the touching tangent line. Okay, because that's actually the section. And then the other examples, like other comparisons, the bottom, it's one of the application in physics, of course, is the velocity, acceleration, but average, like if we travel a certain time in with the certain the certain distance with the certain time, it's extremely easy to find the speed, okay? To find the velocity, no problem. Distance over the time, done. But this is calculus, okay? That's the big thing about calculus. How can I find my speed when I'm driving at that instant? Yeah, it's theoretically, if you will, for example, if you will take a picture of me driving, like at one point, I'm not moving. Yeah, it's kind of like a paradox. We even have like we call Zenon paradox. I think I have one slide you can check later. Like it's the Greek mathematician. He's like throwing the arrow. Yeah, and the same thing. Like if you will take a picture, I think that's the more tangible like meaning you can imagine. Taking a picture, like the arrow is not moving. Yeah, that means, and if I will take in every second the picture is not moving, that means, does it really move? It's going somewhere. Yeah, that means this is kind of like this. The same with the speed at that point. When you're driving and when you're looking at your how do you call it? Speedometer? I think it's the speedometer. When it's showing you the speed at that instant. That means I think it's like amazing. Probably the little calculus guy is sitting behind the dashboard and computing for us the speed at that instant. Because we actually see on that speedometer, we see the speed at that moment. And as I said, speed, yeah, you also know it's a distance over the time. That means at one point, like when I'm driving, at one point, I have no distance and almost no time. Unless I think that is teeny tiny distance and teeny tiny time interval. Okay, that means this is the big big deal about calculus. How to find something that is moving, how to find the rate of change at that instant. Okay? It's like a big game at this point, at one point. Okay. Yeah, I think you will. That's because I know probably most of you, or maybe not most of you, had calculus maybe many years ago. Maybe you can, maybe just recently, and maybe you know all of the formulas. But I always want to like tell you a little bit more what is hidden behind these formulas, because we can memorize stuff, but we have to like understand. Okay, let's. I have another comparisons. What we will do? We will definitely do this one. I think we will not talk about the curvature. We will not talk about this one in calculus 1. I mean, everything is the same, like everything is pre-calculus and calculus. Yeah, height of the curve or the maximum height. Yes, how to find out without looking at the graph, of course, where is the highest point, where is the maximum, where is the optimal solution, for example. Yeah, tangent to the plane, tangent plane to the surface, motion along the line, similar thing. We will not talk about this, but yeah, directing of motion along the curve when everything is changing, the same thing, calculus. And then we can easily find the areas of the rectangle, of something that has the straight sides, And how can we find the area under the curve? If one side is actually curve. Yeah? Also calculus, work and work done by the variable force. We will talk about a little bit about the work. Oh, that's calculus 2. Okay, calculus 2. Yeah, the centroid we will talk, the length of an arc I think we will talk, but that's calculus 2. And a little bit of, everything is calculus 2 actually. Okay, like the surface area of the cylinder or the surface area of the solid of the revolution. Okay, that means something that is not like, let's say, or the volume, where we have the volume. Yeah, like how to find we can find the volume of the like box, no problem, length times width times height. But what about the volume of the loaf of bread? Yeah, like not the square one, not the nice square one, no, just the loaf of bread, like irregular shape. Yeah, also calculus will help us. And this is the last, this is also the calculus 2 actually. We can easily find the sum of the finite number of terms. What about this? How to find the sum of infinitely many numbers? You probably think, oh, it's not even possible. How can I find the sum that I will be adding and adding and adding and adding and keep adding? Yeah, it's still possible. Yeah, the mathematicians, they are crazy guys. They can calculate everything. Okay, yeah, we will do this. If you will take calculus 2 with me, I can show you that secret. And okay, and that's it. That means this is actually the section 1.4, tangent and the velocity problem, which I kind of cover this because you understand the tangent line and you know what velocity, what speed we're looking for. We're looking at that moment, not the average. No. Okay, that means let's go through my slides, which, okay. That means you can see we just said this. One of the mathematicians, of course, extremely important, Euclid, I will say in the German way, Euclid, okay? His definition of the tangent was actually included the verb intersection, intersect, okay? And this actually works if we have circle, okay? Because we can see drawing a line that will intersect a circle once, it's actually a tangent line, always. It's no other option. But when we have more complicated curves, the intersection, the word intersect doesn't work. We know that. We need touching, okay? That we can see. It's not really good definition. And because the blue line, I was drawing this, it's intersecting, but it's not a tangent. But now, one thing, looking at this graph, the pink curve, do you think it's really a tangent line? The pink curve. What do you think? The T, I call T, of course. Yes, Micah, that's actually, okay, that's another concept that we always have to like apply. I definitely see one point and I see another point of intersection, and you will say, oh, it's a secant line. Of course it is secant, but if I limit, yeah, I'm using my magic words. When I limit my like vision, how can I say this? Yeah. Like when I limit the picture that I'm looking at just to the point P, this is definitely a tangent. That means I don't, the second point of intersection, I can think that is far, far away. Okay? Because again, calculus is the whole story at that moment, at that point. Okay? That's we can see. This is the line T, the pink line, it's definitely a tangent line at the point P. Okay? Because it has the same direction. If I will zoom in, I will distinguish no difference. It's indistinguishable. I don't know if between the curve and the line. Yeah, we can see no difference. That means it's definitely tangent at the point P. Please, yeah, please remember that. Okay. What else I have? Oh, too fast. That we can see T is definitely a tangent to the curve C at the point P. You just told me this. And then what I have? Touching. Oh, this is supposed to be with the picture, but we can see the word touching is important, and actually touching means like the same direction. Okay, it's me now. Oh, okay. Let's try to solve the first question. Find the equation of the tangent line, okay, tangent line to the parabola x squared at the point 1, 1. Okay. That's what we can see. From algebra, I can use point slope form of the line because tangent line is theoretically a normal line. It's a line. That means I do have a point y minus y1 equals to m, which is slope, x minus x sub 1. X sub 1 and y sub 1 are simply the point. That means, oh, too fast. That means I can say y minus 1, that's actually slope, and x minus 1. And then I can rearrange to the mx plus b at the end. But what I need that slope. Yeah, that means this is the calculus. That's the thing. Because you can see we do have a point, but how can I find the slope between the point and itself? Yeah? Because we know what's the formula for the slope. Like really basic one will be f of b minus f of a, b minus a. Yeah, we need 2 points. And again, theoretically, I have only a, f of a. I only have 1 point. Okay, and how it's not, we really need 2 points to get a slope, rise over run. Okay, that's what we will do. Because that was, yeah, of course, we will repeat something what the mathematician did so many years ago. That's what do you think? Like, we have to get 2 points. That means what's one of the way will be, do you think we can just simply pick up a point on the curve? Yeah, I would say that's one of the way. And I think I have the parabola, and you can see, okay, I will change in a minute because I have the same parabola. I still have my point 1, 1, and the pink line, I'm looking for the slope of the pink line. But I did pick another point, x, and the corresponding value will be x squared because that's the function. Point Q, and when I connect these 2 points, I have my blue line. I can get easily the slope of the blue line, but the blue line is not really my pink line, but it will be close. Right? Of course, we should have exact value, yes, because something close enough, I don't know if it's good, yeah, as a solution in math. Instead of x and x squared, let's take maybe point 2. Okay, that's mean now we do have original point 1, and I did pick 2, and the corresponding value is 4. Okay, that's mean again, the blue, instead of x and x squared, it's more, if we have values, it's, that mean, do you think you can compute for me the slope of the blue line? The rise over run. Yeah, this will be 4 minus 1, and this is 2 minus 1, which is 1. I have it here. That means what's the slope of the blue line? Thank you. Did I type this? Yes, I typed this. Okay, it's just, yeah, rise over run, 3. And again, it's, I can say it's a little bit less because we can say it's less steep. It's a little bit less than 3. it's quite, yes, quite good. But now I would like to ask you what we can do, unfortunately at the moment using the same method, but what we can do to improve my number, to actually get maybe better approximation. Yes, exactly. Thank you, Noah. We can choose the point. We can choose the point that is actually closer to 1. Because, again, that's calculus. The quantity 2 on the number line, I mean the number 2 on the number line, it's far, far away from number 1. Yeah? We have infinitely many numbers between 1 and 2. That's mean what I did, of course, I went through the integer numbers, 1, 2, 3, 4, but that's far away. I have to be extremely close to the point 1. Okay, that means maybe 1.5, maybe 1.1, maybe 1.01, maybe 1.000001. And then, of course, but what I have, I can't pick 1, of course, because 1 minus 1, yes, the run will be 0, and we can't divide by 0. That we can see I'm getting really, really close to 1, but I do have my limits. Okay, that means my limit is 1. I can go extremely close, but not at 1. And then I can estimate the situation. In this case, the slope. Okay, that means let's do this. It's a little bit long process, but I promise I'm just introducing the calculus to you. I'm introducing the limit process. We will not go through this calculation on the test or on any quiz, no. Because I can, of course, show you some shortcuts. But the idea, okay, the idea is important. That's when you can see this, the tangent line, the slope of the tangent, we can get through the secant lines. We will get closer and closer and closer. Yeah, and that's how we do. Okay. Oh, I didn't. Okay, I should show you step by step, but it's okay. That's what. Let's look at this one. I did pick the point. This is my point 1, and I picked the point 1.5. And the corresponding value 1.5 is 2.25 because we're squaring. And then I can compute the slope of the blue line. Okay, rise of the run 2.5. Okay, now I actually went even closer, 1.1. Okay, and the same thing, rise over run. This is value 1.21, this is value 1. Slope is 2.21. And I went even closer, 1 and 1.01. And the slope is 2.01. That's when looking at these slopes, yeah, you shouldn't see this, I should show you later. Looking at these slopes of the blue line, of the secant line, 2.5, and then 2.1, 2.01, that's what do you think? What will be the slope of the tangent line? Like approximately. Of course, I did. Yeah, that means if we will go extremely, yes, extremely close, we can see I can't have 1 and 1. 1 minus 1 will give me 0. That means, yes, thank you, Noah, it will be 2. That means that's actually the way to do it. To find the slope of the tangent line, it will be the limiting position of the slope of the secant line. And we can do the same calculation on the left-hand side. Okay? We can approach 1, like from the left, 0.5, 0.9, 0.999, 0.99999, even closer. And I can show you 0.5, 0.9, 0.999, and that's the values of the slope. Slope of the blue line is 1.5, 1.9, 1.999, and of course, when we get even closer, it will be almost 2. Okay? That means that's actually the way, but as I said, we will, because I believe we need a calculator for this calculation. No calculators in this classroom. That means I can show you, of course, a little bit different method, but that's the point. That's the definition behind. And, too fast. That means this is extremely important. Yeah, from section 1.4, the slope of the tangent line. And this is probably the first time I did use that word. The slope of the tangent line, again, is the limit of the slopes of the secant lines. And now we do have a symbol, okay, to do this. That means limit, we will use just the abbreviation. We will use just LIM, lim. And underneath, because the whole process that I just did about for the previous two slides, yeah, I was limiting. I was getting closer and closer to point 1. That means I was limiting, and what I did again, I was taking point Q to be extremely close to the point P. That means the x coordinate of the point Q was approaching point P. Okay? And then limiting the limiting position of the slope of the secant. That's slope of secant. Okay? And then we do the output was, slope of tangent. Okay. And one more thing, probably you will think, oh, I should actually say like approximation. Yeah, because we kind of approximate, making the whole process, going through this whole process, I approximate. But we will use the normal equal sign, because the whole approximation process is hidden behind the limit. That means that's the limit definition. Okay? And now what I did, I make more rigoristic, like math symbols. That means this is the same thing in that box, the same thing as this, but just using symbols. Limit Sx, which was the Q point, is approaching 1, was the P point. And this is just the formula of the slope. Rise over run. F of B minus F of A, B minus A. And we did get 2. And please note, this will be not, yeah, we will just write equal sign. But we got through the approximation. And then this is just algebra to finish the question. The equation of the tangent line, because we will say point slope. And if I will distribute everything, we will get to x plus 1. But the point is to find the slope. Okay? Okay. I think we good. And we will practice a lot. But please have this idea. Okay? And one thing in this section, like just the same concept, but the application, which we talk about this, velocity. Okay? That means this is, the picture should be I don't know why my slides. Okay, that means, as mentioned before, it's no problem to compute the average velocity, average speed, but probably it's more challenge to compute the instantaneous velocity. Okay, that's we remember that picture from one of the first slides. Average, no problem, because I can simply say it will be distance over the time. I do have my distance, I do have my time. But what about if I have just one point of time? That means distance is, then I can say distance is almost 0 and the time it's almost 0. Yeah? It's something like a slope of the tangent. Do you remember? Because we have no rise, no run. Yeah, we make teeny tiny rise and teeny tiny run. That means the same we will apply here. So let's look at, I think I have this graph. Let's pretend that my position function is defined by 10t squared. Okay? And I'm driving, and after 1 hour, I drove 10 miles. not really, probably really slow, but it's okay. 1 hour, 10 miles. This will be in miles, and this is in hour. After 4 hours, I drove 160 miles. Oh, and we can see I increase. 160, did I mess up the 60? Can you tell me the average, my average speed? What will be the average speed, average velocity? Between 1 and 4 hours of my trip. I just need this distance, okay, which is 160 minus 10, because between 10 miles and 160 miles, I drove 150 miles. And how many hours between 1 and 4? Yes, I see the final answer. The time interval, of course, is 3 hours. Of course, 150 miles over 3 hours, it's nice miles per hour, 50 miles per hour. Yes, thank you for your answers. That we can see, no problem. But what I would like to point, which actually I typed this, computing this average velocity between 1 hour and the 4th hour of my trip, we just use simply the same concept like a slope of the secant line. Yes, rise over run, or I can say f of b minus f of a, just using the general notation. Okay? A, b, f of b, f of a. Okay? That means the same idea. And I type this, the slope of the secant line is just the average velocity. If we have this distance on the y-axis and the time on the x-axis. Or I can say just the general average rate of change. Okay? Average rate of change. Okay. And because the rate of change, but average is still algebra. And now my question is, how can we find the speed exactly at one point? I mean exactly at one point, and actually exactly at 1 hour. I'm driving at exactly at, let's say I start at midnight and exactly at 1 a.m. Yeah? What is my speed? That means mathematically, the question we can transform and we can say, oh, it's exactly the same thing, like computing a slope of the tangent line. I mean, I can't really find my distance and my time having just the data at 1 p.m., at 1 hour of my trip. I really have to probably find how the car moves, like let's say 1 hour and 0,000, like in a few seconds. Okay, and then the distance, of course, this we remember, this was 10 miles. This will be like 10.0000, tiny, of course, tiny, more zeros. Yeah, that we can see. I have really tiny time interval and extremely tiny. Probably my wheels not even moved, but that's the way. Okay, and slope of the tangent line will be exactly the same concept, the same question asked, like instantaneous velocity, instantaneous rate of change. Okay, instantaneous rate of change. Okay, and we will not do this calculation. I think I have the I mean, I can write, okay, that's mean to find the slope of the tangent. Let's say this slope of the tangent, it will be a limiting position, okay, and the time must approach 1. So we can see we will approach 1. 1.01, 1.0001, or maybe 0.9, 0.999, we can do from both sides. And that means the limiting position, the time is approaching 1, and the slope, f of b, f of a, slope of the secant, b minus a, which I can write, okay? of course, A and B, this will be 1, and actually the value is, if this is A, 1, then this is f of A. Okay, that means this is 1 and 10, and this will be t, I don't know, it's close to 1, and this will be my function, 10t squared, the value. Yeah, because if t is 1.01, then I will substitute here to get the value. Okay, that means this is the proper definition of the slope of the tangent line. Yeah? The limiting position as time is approaching 1, this is like an arrow. And we can compute. But we will definitely compute this. We have to wait until section 1.6. Okay? But we know the concept. Okay, that's actually everything from section 1.4. I also want to touch section 1.5 today, okay? And tomorrow evening, we will focus on section 1.6, which I believe you will really enjoy because we will just computing. We will compute, but we still can't forget the meaning, okay? Okay, we will skip this. Maybe you can give me the answer to this one, because this one, I think I asked this once on the midterm, similar question, okay? That means let's see if you understand. Let's wrap up section 1.4 with this question. That means let's read. Use the sketch of this function y equals to f of x below to find the sum, okay? We will add at the end the sum of instantaneous rate of change at 7 and the average rate of change on the interval from 0 to 2. That means, first of all, who can tell me, because that's interesting, what is instantaneous rate of change at 7 looking at this graph? I can give you a few seconds. If you know the answer, you understood everything what I said. Instantaneous rate of change at 7. Okay, Corey said 2, Matthew said 2. No, I'm not asking, okay, because you're looking at, I'm not asking for the value. Yeah, because I think we can say, I am not asking that's okay, f of 7 is 2. I am asking what is happening. Okay, I will tell, like I'm asking for the instantaneous rate of change. Okay, and I see the answer is 0. Because do you remember instantaneous rate of change? Shall I come back? Instantaneous, this is instantaneous rate of change. Instantaneous rate of change or instantaneous velocity is exactly the same thing like slope of the tangent line. Okay. That means I will write for you, and that's important. Slope of tangent at that point. And I can write. That means I see that's my point, and drawing a tangent, I believe I will draw a horizontal line. That means I don't really need to do that approximation. We nicely see. That means, yes, this will be 0. That means that's the value, 0. Okay, that means please remember instantaneous rate of change is a slope of the tangent. And using the same meaning, the same understanding, what's the average rate of change? Mathematically, will be slope of what line? Can you type for me? Average rate of change is just the slope of, I'm waiting for my students to type. Oh, average. Average, we need 2 points. Oh yeah, okay, between, oh no, I'm just, the name. Yes, the secant line. Oh, you're looking at the values. Okay, no, just the general, and then we will compute. Slope of the secant line. Please remember. And of course, secant line, we need 2 points. And that's not calculus, that's math, important math, but the green part is the calculus. Okay, that means between 0, the value for 0 is here, the value for 2 is here. It means I will connect these. And do you think you can tell me the slope of this line, the red line? It's negative, and it's 4/2. I think it's -2. Yeah? Yeah, I'm just trying to, okay. That means one slope is 0, another slope is -2, and the only thing that they ask the sum. Let's say S. That means the final answer is -2, because we can see we have to find a sum. It's just additional thing to ask. But of course, the important information on this slide is the slope 0. Please remember, instantaneous velocity or instantaneous rate of change, it's always the slope of the tangent line. If we can't find the slope, yeah, then, I mean, we can always predict numerically or graphically. Yeah? And as I said, we will get to the point that you will compute really fast. You will see. Okay, that means that's everything for 1.4. Oh yeah, that's the Zenon paradox. You can read this later. Oh. Okay, but we do have here 15 minutes. I think we can manage at least to introduce. Okay, that means section 1.5 still talk about the limits, but the limit of the function. That means what we will do. That's the order of in the textbook, but I think it's okay because the whole tangent concept. Yeah, we will still have it, but we will actually take this and we will start chapter 2 again with the tangent concept. But just what I explain everything, the limit concept we're taking now, and we will expand this more. Okay, that means the tangent line concept, we will start chapter 2 with this, and from this section, from section 1.4, we will just take limit concept. That means now we will try to find a limit, okay? Evaluate, probably you will say estimate, approximate a limit of the function, okay? So let's see. That means the intuitive definition, because we're not covering section 1.5. No. 1.7, I believe, which is like the exact definition of the limit. That's too crazy. Okay, like a delta epsilon. We will just nicely talk about the intuitive definition, which I believe is so important, yes, to understand. Okay, that means we learn that the limit means like we're getting close enough. We're making some approximation, estimation, rough calculation. Okay? Of course, guess. Let's say educated guess. Okay, not the wild guess. Okay, that means the limit of the function. Okay. Also, we remember from the first slide, this is just the value. That means this is fine. Value of the function at C will be f of C. That's not a problem. And we do have a dot. But now we have to compute, and I will write this, limit. Okay, limit means like we're getting close enough. We will approximate function. That means how this curve, okay, behaves as x is approaching C. Okay, and we can even see we do not have that point. Yeah, it's open. I will maybe make more. Yeah, it's like it's not a solid dot. It's an open dot. That means we can't really. we can't really compute f of c like here. Okay? But we can also notice that both of the curves on the left and on the right hand side, they look the same. Okay, but what we have to do, as x will go extremely close to the point C, we will get really close, really close on the left and on the right hand side. We have to figure out at which point, okay, at which level, at which y value is that open dot. Yeah. Probably the value it's connected, it's probably similar, okay, but that's the thing. We have to get like close enough and get simply the height where the open dot is at. Okay, and let's look at more. Okay, that means before I show you like a notation, let's do this exercise. Okay, we will investigate the behavior of the function. Again, x squared. We like function x squared. Okay, you remember probably last week I said that we will use a lot. That means this is function x squared. Oh, we shouldn't have these arrows. I just don't like it. Please remember, when you draw your xy plane, I'm really sorry, I should always put the arrows in one direction. Okay? Never. That's actually, I know that some of the textbook is doing this. No, as soon as you reach calculus 3 and you will have x, y, z, like we even like using this, probably you remember maybe from physics, we always pointing the positive way, because the x, y, z, like this number lines are kind of like a vectors. We only pointing one direction. The increasing, the way that is increasing, the positive. We know that is going in the negative direction, but we never put the arrows. That's actually not good. Okay, never mind, we have x and y. And we do have a nice function. We know this is x squared. And what I want to find out how this function behaves close to 3, not at 3. That means I will pretend that I don't have this value. And we're looking at that level. That means what I have a table, okay? Because that's the same process, the limit process. X, okay, will go extremely close to 3. This means that x is approaching 3. From the left-hand side or from the right-hand side. That means you can see, I can pick the point 3.1, 3.01, 3.001. Okay, and that's the corresponding heights, the corresponding value. And that means I will have the value 9.61 and then 9.06 and even closer 9.006. And then from the left-hand side, 2.9, 2.999, 2.99, and that's the corresponding points. That means, what do you think? What is this? What will be my question mark? How function behaves at 3? Probably you will think everything is crazy because the answer is obvious. Can you tell me that question mark? Can you tell me that answer? Oh, yes, of course. That means I can say, again, kind of like, this is, I will write a little bit nicer. It's approximately, it's 9. And I will maybe remove everything. And if you can imagine, yeah, this like kind of like an open dot, the open dot is exactly at that level. And this level, of course, is 9. The value of the function is 9. I don't want to, I will just put 9. Let's say green, 9. Okay, that's what we can see. It's not exactly 9, but we can see function is approaching this curve, approach that dot, and that dot is at the level 9. Okay, but again, we kind of did through the approximation. Okay, and now the formal way to write this. That means we will say this: limiting position of the function x squared as x is approaching 3. We don't know, okay? But of course, we know that it's 9. We also know that the value is 9. But now, probably the weird moment, this 9, let's say is the curve is approaching. Let me say this. But this 9, the red 9, yeah, it's exactly the value. That means just, yeah, maybe you can like watch this again, or you can like digest this, you can read, of course, the section in the textbook. I really would like to tell you that the green 9 and the red 9 are a little bit different, okay? Because the red, this is just the value. We are exactly at 3, okay? And the value is 9. No problem. Now the green is telling me that the function is approaching 9. And I don't even have to know what is happening exactly at 9. I know that the curve approaches that red dot. And this red dot could be even empty if I'm just focusing on my limit. Like if I'm just interested what is happening next, like near to 3. Because we can see we can take all of these values close, or all of these values like which are close, really, really close, and we know that this is approaching the height, the level 9. Okay, I hope this is like clear, but please remember they are a little bit different. Of course, we will use this concept like I will say, oh, this is 9 and this is 9, they are the same, okay? But I still want you to understand that the green, the limit is a little bit different. We are not at that point. We are close, we are approaching 9. And the red is just the value. Okay, that's the whole idea. Limit always means that we are close, really, really close to the given point. Okay, and then let's look at this nice description. Oh, too fast. That means that's how we will express, how we will read this. Again, the limit of the given function x squared as x approaches 3 equals to 9. And you may notice, again, that's green. Yeah, green, good. I will say equals to 9. Okay, but we know that it's not exactly 9. It's different than this 9. Yeah, that's value. But the limit is the limit. We approaching 9. And then I have general statement. Okay, limit of the function f of x as x approaches a equals to L. And you can pick any description, any way to express this, to say this. That's when I think I said the first option. You can read this and understand this as the value of f of x tend to get closer and closer to number L as x gets closer and closer to number a. Of course, we're talking about, I can even, let's say this. This will be the a, and this is the L value. Okay, and as x approaches a, we can see the curve. Yes, we're getting closer and closer on this side and on this side. The curve is definitely approaching the open dot, and the open dot is at the level L. Okay, and that's the limit. That's how we will compute the limit. And that's the thing, that we can still find the limit, the behavior of the function at the given point, even if this point is not in the domain. Even if the function is not defined at this point, we can still compute the limit. Yeah, we will have no value. Like in this case, let's say the open dot, the value at A, it's actually undefined. Okay, the value at A, because we can see no value, open dot. Okay, and I have one exercise that I would like to finish this section. Yes, is this one. Okay, it's from your textbook, but looking at these graphs, 3 different graphs, A, B, and C. I would like you to tell me what is the value at A and what is the limit of the function as x approaches A. And let's just look at the difference. This is the continuous function, no gaps, no holes, nothing. This one, can you see we have an open dot and the value is somewhere else. This one we have open dot and no value. Okay, that's me. Let's get ready. I need 6 values from you and we will finish. Okay, limit of the function f of x. This is of course function f of x, right? Did I stay? That's f of x, that's f of x. That's me looking at A. What will be the limit of this function as x approaches A? Do you think you can? Yeah, that's we can see. We're getting closer and closer to A and the function is approaching, yeah, I don't want to, that level, L, good, L. In this case, what is f of A? What is the exact value at A? It's of course L. Really good, we can see. Because I can even draw the solid dot. Solid dot is important for the value. But I can say with respect to the limit, the function is approaching that dot. The solid dot or the open dot doesn't matter for the limit. Okay, now let's look at the middle function. What is the limit as x approaches A of the f of x in the middle function? What do you think? Limit, yes, still limit. We're still looking what function does, like how the curve behaves. Of course, L. What is the value, the exact value, the solid dot? Is at the level M. Thank you. Okay. Okay, that means you understand like how function behaves. That's the limit and exact points. And now the last curve. What is the limit of the function as x approaches A? It's, yes, of course, even if we have the solid dot, it's still L. What about the value? It's undefined. D and E, we will say does not exist. Okay, that's mean, yeah, it's undefined. Thank you, Micah, that's good. Because we can see we have open dot and I don't have my solid dot. That means the value simply is, yeah, doesn't exist for this function. But you can see the limit is always L. And if you look like from the distance, if you look at these graphs, they behave the same. That means, of course, the limit, the behavior of the function must be the same, almost at every single point of the domain, or even like even if it's not on the domain, we can still find the limit. Okay, I do have a few more problems, but we can, yeah, we can probably, this will be we can start tomorrow night the session with, yeah, with these problems. Or maybe, hang on, maybe, because since we're talking, I know that probably you have to go, but let me show you. Oh yes, I have. Okay, I will finish tomorrow. Okay, I don't want to keep you in a rush now. I will finish tomorrow. If I not finish the section tomorrow, which tomorrow will be just the practice, then I can provide for you some additional practice. That's not a problem. But I will start from this slide. I will start the session tomorrow. Okay. That's mean, thank you very much. Thank you for joining me. Thank you for answering my question. And I hope you understand the limit concept, the fundamental concept of calculus. Okay, thank you. Thank you. Please be active, start typing stuff on the discussion. Okay, thank you.